In this video, we'll talk about how enols and enolate ions, we'll talk about what that is, form from ketones. So starting with a ketone, how does that mechanism look like to form the enol? And that can occur in acidic solution. So if we have acidic solution, we actually don't form the enolate. The enolate forms in basic conditions. So we'll cover that as well. Let's do an example with acid catalyzed. We'll say enolization. So we'll start with a ketone, form an enol in acidic conditions. So let's say we start with acetone. So we have our ketone. We're in acidic conditions. So if that's water, we'll just say that's water. We have this acid present, H3O+. H3O+ or some acid in the presence of a ketone. First step is protonating carbonyl oxygen. Of course, we know that now this carbonyl carbon is more susceptible to nucleophilic addition. We've activated the carbonyl. We can show that formally through resonance. So we'll show resonance in green here. So now we have a positively charged carbon. Now to form the enol, if we have water present in solution, instead of adding directly to that carbonyl carbon, that would give us a diol as the product. But the mechanism to form the enol involves one of the hydrogens in one of these CH3 groups. So the two CH3 groups are equivalent, so it doesn't matter which one you show. What happens here now is that water, neutral water, can deprotonate this carbon, and the electrons in the carbon to hydrogen bond will form a double bond between the two carbons. And so that gives us our enol. So we have our alcohol group here, and we have our carbon to carbon double bond. So here is our enol, starting with a ketone. So this occurs, this is how the ketone tautomerizes into the enol when the conditions are acidic. When conditions are basic, this process looks different, and it's helpful to consider what we will call the alpha hydrogen acidity. And this is how we form enolate ions. So we're shifting from acidic conditions to basic conditions now, and we'll show how the enolate ion forms from a ketone, and then eventually we'll show how that enolate ion forms then the enol. Okay, so we'll focus on the carbonyl alpha hydrogen acidity. So if we have a ketone, remember the carbon bonded to the carbonyl carbon is the alpha carbon. So here's our alpha carbon. A hydrogen bonded to that alpha carbon has some level of acidity. So it's not very acidic, but it is more acidic than typical hydrogens bonded to carbons. So if we have a base present, we'll just say B to abbreviate the word base. We'll say it's a strong base, negatively charged. This base can remove that alpha hydrogen, and then we put electrons onto the carbon. So the alpha hydrogen here, if we're talking about the alpha hydrogen on a ketone, the pKa is about, depending on the structure, 15 to 25. Not a very low pKa, right? This is not a strong acid, but it is a lower pKa than many other hydrogens that are bonded to carbons. So and we'll explain why. So due to ... Let's draw some structures and then we'll finish off that sentence. Okay, so if we have a strong enough base that can remove that alpha hydrogen, then the resulting structure looks like this. We have a lone pair on a carbon. This carbon is now negatively charged. Carbon is still bonded to carbonyl carbon. Well, with that negative charge on that carbon, we can show resonance here where that negative charge forms a double bond between the two carbons, and oxygen is negatively charged instead. And we know oxygen's more stable with a negative charge than a carbon is. So this is an important resonance structure. So let's draw resonance here, where instead of the negatively charged carbon, we've shared the electrons with the adjacent carbon, and then now we have a negatively charged oxygen. And this here is the enolate ion. So enol, because we have the carbon-to-carbon double bond and the oxygen, but enolate indicates that the oxygen is negatively charged. So this is the structure of the enolate ion. So the reason now, going back to that alpha hydrogen, why that alpha hydrogen has a pKa lower than many other hydrogens bonded to carbons, this is due to the resonance stabilization of the conjugate base. And the conjugate base is that enolate ion. There's also another effect that causes this pKa to be lower, and this is the polarization or the polar effect. If you look at this first structure here, we have a negative carbon. So this structure that I draw the arrow to, we have the negatively charged carbon, and remember carbonyl carbons have a partial positive charge. So having the formal negative, partial positive near each other, that's a stabilizing effect. So due to resonance stabilization of conjugate base and polar effect, specifically the partial positive carbonyl carbon. Next to the carbon with electrons and the negative charge. Now you might imagine, and in the future we'll talk about this structure here we have a carbon with a negative charge with non-bonding electrons. This is a nucleophilic carbon. The nucleophilic carbon can act as a nucleophile, so this could add to other electrophiles. So we will come back to that in future videos. So let's show now, if we are starting with a ketone, we'll do an example under basic conditions to show how we will first form the enolate ion and then we'll end with the enol. So here's another example. Base-initiated enolization. So remember earlier in this video, we did the acid-catalyzed enolization. We started with acetone as the ketone. We have acidic conditions, and we showed how the enol formed. So we'll start again with acetone. But we will have strong base present, so we'll say it's a hydroxide ion present. And that hydroxide ion is a strong enough base to remove, the reaction will be in equilibrium, but it could remove an alpha hydrogen. So we'll show that alpha hydrogen on that carbon on the right. This carbon is still an alpha carbon because it is bonded to the carbonyl carbon. So the hydrogen that we've emphasized is the alpha hydrogen, or is a alpha hydrogen. So our strong base can remove the hydrogen, electrons go to the alpha carbon. And we've generated one resonance form here of the enolate ion. We have a negatively charged carbon. This resonance form shows the electron density at the carbon. We'll draw a resonance again, same arrows as we did above. The negatively charged carbon can create a double bond between the two carbons, and we break that carbon to oxygen pi bond. So drawing the other resonance contributor, remember both of these exist in reality. A hybrid is what the molecule exists as. One resonance structure shows the electron density at the carbon. The other structure shows electron density at the oxygen. And then remember, this is our enolate ion. So if we're in basic conditions, the basic version of water, OH-, removes the hydrogen. Neutral version of water can then donate a proton, and we get our final enol form. So we formed the alcohol group. We have a carbon to carbon double bond, and carbon is bonded to 2 R groups. So in basic conditions, if we're starting with a ketone, we form an enolate ion, which has a nucleophilic carbon. We have acidic conditions, which we showed first. Then we don't form the enolate ion, but we do still form the enol through that acid catalyzed mechanism there.